So, okay, I am not a physicist. That's the first thing I have to say. And I'm trembling speaking to a physicist audience because I consider myself numerical mathematician, computational mathematician, and my business is algorithms. But you dig deep enough, and behind every algorithm which I do, I find some physicists developing it in 19th, 18th, 17th, 20th century. So it's lovely to work in an area like this. But also, when you speak about your algorithms, I had a great pleasure listening to all the talks in this conference. You guys attack one, well, not one, of course, but more or less the same problem from different methods, from different sides, using different methods, different models. But you have plenty of physical intuition about it, plenty of things you can look at. And when you communicate, you talk about these things you observe about the behavior of your physical systems. You never change from the language of your physical objects of interest, and that's how it should be. And you develop these matrix product states to describe as the models of your quantum systems, and they appear quite naturally because your Hamiltonians appear already in this tensor product form. Yes, so you have a direct product of something, of some one-side operators here, then you have a sum, and you figured out that you can arrange it very nicely in this form of a matrix product state. So this is a great thing to have in a community as a model and as a precursor to developing effective algorithms. We sort of rediscovered it in numerical neuroalgebra back in 2010, and we discovered the connections to physics. And as I said, it's since then I always feel myself like an imposter talking to a physical audience because you guys invented this, and we just maybe rediscovered it at some point. But when we develop it in numerical neuroalgebra, we develop it with the purpose of giving this as a tool to people who are going to apply it in other disciplines, computational biology, medicine, you name it. And we don't have as much physical insights about these disciplines. And maybe people working in these disciplines also don't have quite the same way of abstracting these ideas as we would like as mathematicians. So we want to develop algorithms so that they are, in a way, problem agnostic. Just like solving linear system was problem agnostic in 20th century. You just give people a solver and you ask them to provide a matrix and maybe a preconditioner. And then the solver just solves it for them. Yeah? So this level of abstraction of a method from a problem is what we are aiming for. And this, of course, you may think it's completely silly because your power is in actually exploiting those symmetries and physical properties and area laws and things you know. And I would want partly to abstract from it and give user a way of using it if they have it, but also design an algorithm that it remains robust and effective and fast, even if we don't have all these wonderful things which make it fast for your physical problem. So I will show you two examples today of how lucky we were, in trying to implement this idea. It all will be in a context of a linear matrix product state. So our model for now is just a linear MPS. But we apply it to what we call a high-dimensional problem. So we apply it for epidemics on networks. And this is, of course, motivated by, to me, a huge change to the way how we live in the past 3 years. And it will be a non-familiar problem, but with a familiar method, which is basically your one-side de-Merogy with a little twist. And I will talk about this little twist a little bit because I think it makes things better from algorithmic point of view. And my second part, I'm sorry for trying to twist two topics in one talk, but my second part will be talking about less familiar. Maybe the problem will be familiar, but the methods will be definitely less familiar. And we will be talking about interpolation and integration of a high-dimensional array, which appears in many contexts. So this will be familiar method for unfamiliar problem, and this will be maybe unfamiliar method for maybe familiar problem. Yeah. So let's see what you like most. Let's start with the first one. It's an epidemics on networks. Okay. So when you talk about epidemics on networks, and 3 years ago everyone became an expert in this topic very much. So people mostly show you this comportamental model, 3 differential equations, and you probably already sick of it. So I'm not going to comment on this very much. And this is comportamental description of a well-mixed model. So you assume that everyone is in contact with everyone, and you measure people in every group by a real number. So you can have 3.5 infected and 0.5 susceptible, for example, very far from physical reality. You can try to move closer to physical reality and then describe your states by saying, I have 2 infected and 1 susceptible, for example, but then they are integers, they are always integers, and you move from one state to state. So you talk about probabilities of every state, and you talk about a rate with which these probabilities, flow into each other. So this is going to end up with n²/2 differential equations, slightly harder. So if you're trying to solve it with an undergraduate student, they will struggle a little bit, but it's a better method because it's closer to physical reality. But both of these methods, they assume that your system is well mixed. Everyone is talking to everyone, yeah? So let's first of all see that even these 2 approaches give you different results, yeah? So you have a comportamental model here in dots, and you have a probabilistic description here in a solid line with the standard interval around it, and they are different. So you want to be closer to physical reality, you need to solve more differential equations, but you obtain something which is probably more accurate, yeah? So now this well-mixed approach, which many people assume is of course not true for people, yeah? It was true for animals in their housing when it was discovered, proposed in 1930s, but it's not true for people because people do not live together, yeah? They don't interact all to all, so you have a network of contacts for people. And this means you cannot describe this as by talking about sizes of each compartment because geometry is very important. An affected person in the middle of a network is much more potentially harmful than an infected person on the side of a network. So you need to talk about probabilities of states. And this is, of course, very close to your heart because this is just exactly the sort of wave function analog. Yeah? So you talk about probability of every state. And you have 3 to power n states because you have n sites, and each site can be in 3 different positions, susceptible, infected, recovered. So it's 3 to power n states in total. This is very close to physics, of course. And then we solve it. So we can write down the transition matrix, how these states flow into each other, and you solve people in this business called chemical master equation. You will call it time-dependent Schrödinger equation in real time, but you solve a time-dependent equation with exponentially many differential equations here, yeah? So it's difficult because there are exponentially many equations. We need to store all this probability density distribution together. It has many variables, and it's all our business, all our reason for apply matrix product state to simplify this problem, yeah? So just before we continue, I will show you that it makes sense. Here I show the difference between well-mixed model on top and network model, the chain model on bottom. It's just 3 people, but you already see the difference. So you may not care between, if you have a well-mixed model, you may not care about this difference, but you definitely should care about this difference because it describes a real effect, the effect of having a network of contacts rather than all-to-all interaction. So we want to describe it. We need to solve a much harder equation. People really don't have many tools for this. They have, I would say, 1 tool, and we want to propose another tool, yeah? So what is behind this tool? Of course, the idea of separation of variables, which you know very much. So for us, it's just a generalization, a low-rank approximation. Yeah? So you have a low-rank format for matrix. You compute a SVD, let's say, or any other low-rank truncation, and you separate a row index of a matrix from a column index of a matrix. Yeah? And you have a summation index alpha, which sits in between and glues rows and columns together. That's a low-rank format. Now you want to generalize it to high dimensions, you get your MPS. Yeah? You have a sequence of blocks, and they are glued by these indices, summation indices, bond dimensions. Yeah? And each box has information about just one side. Yeah? So this is very familiar. Of course, train. Yeah? So we just called it tensor train when we rediscovered it because we didn't know about MPS when we first found it. Then we realized the connection, but we call it tensor train because it just connects the network in a linear way, just as train would do. You use these representations very much. We like these representations. I will be using this representation because for me, I care a lot about the bond dimension. Yeah, in many of your applications, just set up the bond dimension and optimize. But I want to adaptively choose the bond dimension in my algorithms. And for me, it's important because I don't know what bond dimension the problem is going to have. I don't have as much intuition about how it's going to affect the accuracy. So I want my bond dimension to adjust to the solution and in optimal way find it adaptively during the algorithm on fly. So I'm picturing it like this because I will be drawing these matrices and how they increase and decrease. For me, this is going to be important. Okay, but this is very familiar. So how we solve problems, yeah? How we solve eigenvalue problems, how we find ground states, how we solve even linear systems. Yes, please, Geoffrey.
Can you specify what you mean by n in the example that you were talking about?
Capital N.
Yeah.
It's the number of your sites, and if we go back to example, it's number of people in the contact network. Capital N, yeah, capital N people in the network.
And the three options is each person being
susceptible, infected, recovered. Okay. Yeah. Yes, please.
So is the ansatz that the tensor train squared is the probability, or you just that itself is the probability?
This is the probability.
So do you have to worry about it will be negative in general, or?
We may have to worry about this being negative, and we really, and we must. And we have slight issues about this, and if we do, we will switch to ansatz when this represents a square root of a probability, and then we can recover from it. So, but in this talk, we don't have this part of the discussion. Yes, please.
The elements of your tensors, are they generically positive, or will you have situations where
No. They are real numbers. They can be complex numbers as well, but...
No, but I mean, that can they be negative, or
real numbers, yes, mean they can be negative, yes.
Okay.
Yes. Yeah, they usually come out from SVD, so can be anything. There is a lot of orthogonality here, for example. You know, as we know, it's important for truncation. Jeffrey.
You said that your network has n people, but are you assuming any specific connectivity between them?
We will, yes. When we solve direct problem, we will assume connectivity and predict the probability of transitioning into particular states. All of them, actually, all the states. Yeah.
And your network, those n people, are they contact? Do they know each other in a similar way?
Yeah. Excellent question. Yes. So no, sort of. Well, no. We need to implement it as a tensor tree at least. Yeah, and then it's all our algorithms will have potential of being implemented as tensor trees, but not as general tensor networks because we do truncations, we do approximations, and loops in a tensor network are problematic. But I keep it linear for the sake of simplicity, and because we don't have yet implemented it, we haven't yet implemented it as a tensor tree. We know that we should do it at some point. This is something we have not done yet. But we keep kind of an open mind about this, and we try to design the algorithms which will be easy to generalize on the case of tensor trees. But in this talk, I am not using it, so my results are not going to be particularly, if my results are bad, it's not because the idea is bad, it's because I am doing it in a stupid way here. But I want to focus on something else here and show you some other tricks which actually make it not as bad, even though I don't match my tensor train geometry to the problem geometry as well as I should. Yeah? Okay. So how do we solve problems like this? I will describe it through a variational ansatz. We can optimize over one site at a time without changing the bond dimensions, and this was known for, I don't know, for centuries probably. It's a very long idea. You optimize just blocks one by one. Of course, the problem is you cannot change the size of your tensor manifolds. You cannot change the bond dimension. It converges sometimes, but it mostly stacks in local minima, so it's not an algorithm I would recommend. But at least some analysis of convergence is possible, and some people in our community have done this. But that's not a practical algorithm, I don't say, for many applications. To make it practical, you need to adjust the ranks. And I think the thing which make it work was, of course, the proposal of demerge algorithms, that you combine two sites and then optimize over a pair of sites, and then do SVD to split them and optimize your bond dimension at this stage. So optimizing the bond dimension, the rank is very important. I call it TT rank, by the way, so I'm sorry if I keep using this word. But the dimensions of your tensor manifolds change at every step, so it's difficult to make a formal analysis of this algorithm. But it works brilliantly well. Yeah, it has ability of finding the ground state really, really nicely. And you can apply it to ground state, to eigenvalue problems, to linear systems, all the same. It's just the same geometry, just one-dimensional problem changes, but the rest is really the same. So Jeckelman, I think, was the first who realized you can solve linear systems with this, and then we also sort of solved it, and then I will show you what we did with this next. So this is a little twist which we want to do. In your applications, the mode size, the number of states for each mode, for each variable, is usually small. You have quantum states, so it's 0, 0, 1, up and down, 2. But in our applications, it can be larger. It can be a quadrature on a physical space, so it can be 100 or 1,000. So optimizing over one site or over a combined supersite involving two mode dimensions is a big difference for us. We want to keep it one site, yeah? But we want to adapt the ranks, and we want to have some proven convergency properties. So how we achieve this, that's how. We optimize over one site, and then before we proceed to the other, we insert a gradient information in the first site. We compute a gradient of our problem, we compute the component corresponding to this block, and we put it here, and we put just zeros here. So we haven't changed the state which we represent, but we added some extra space in the environment, some extra directions in the environment, and the directions are pointing us towards the gradient direction, which guarantees a global convergence. So these end up being very useful. We keep optimizing over one site, and then we compute the residual, compute one component of it, and just insert it here, and insert zeros here. Yeah, please.
Two questions. One is that specific, I guess that's not specific to the linear solver problem, LinSolve problem, but that's what you're showing.
The one-site problem is agnostic to the expansion step, yes. So the expansion step is a residual. Whatever problem you have, insert a gradient direction here. It will be good. But then whatever you solve on an optimization step is orthogonal to the idea, yes.
And then is this basically an alternative to doing a two-site update?
It is an alternative to two-site update of
demergy,
yes. That's a proposal, yeah, okay. Yeah. And compared to demergy, it ensures theoretical global convergence, which I think theoretical results we never had before, I don't think. It, in practice, converges faster than demergy, and not only because we have optimization over one side, but also in terms of iterations. Yeah, so not only in real time, but also in terms of iterations. And it can be also applied to time-dependent problems, as I will show later. Please.
Why is the gradient not 0? Like, don't you solve x exactly to make this equation 0?
We solve a one-side problem, exactly. Yes, but then we compute global gradient. But global gradient is not 0 because we haven't converged to the steady state yet. Yeah, we just optimized over one side. But global gradient, if you think about global problem, is not 0, right? Because you are not in the ground energy yet. Yeah? So you think about computing global gradient, but then using over only one component, one side. So think about computing global gradient as MPS, but using only one side of the global gradient. Does it make sense? You compute a projection of the global gradient on one side.
It seems like this is the thing that you're supposed to be optimizing in this linear problem.
No. The global gradient is not 0. If it was 0, I would be in a steady state already, right? In a global minimum, but I am not in a global minimum. When I optimize over one side, I am not in a global minimum. I still have ways to go. So my gradient is non-zero, and I just compute a component in the representation of this gradient in an MPS.
The gradient with respect to the first answer over there, after solving this linear problem, this thing should be 0.
Use your seat mic for the people on Zoom.
I'm sorry, yes. The gradient with respect to the first tensor
No, it's not a gradient with respect to the first tensor which I compute. I compute this. It's a global gradient. It's a high-dimensional vector. It's a high-dimensional state which I compute as an MPS and then use one component of this MPS. But can you agree that this is not zero?
Yes.
Yes, so I compute this and use one component of this, and use one side of the gradient.
This thing is not zero.
It's not.
Projected onto, like everything projected out except the first tensor,
Yeah,
this should be zero.
no.
That's the thing that the linear problem.
If this was zero, then the whole thing would be zero because it's a product.
That's what I was thinking.
But this is not zero, so this can't be zero.
Good.
I'm sure he's implemented this before. I mean, it works.
No, I mean, it's a valid question. It's a valid question. So it's
I'm
just
sure indeed
and you really it's a smart. There was another one, yeah.
Compare this. So Steve White addressed this problem of single-site DMRG not being able to grow the bond dimension with something he calls density matrix corrections, which does exactly this. You act with H on the state, and it gives you ansatz for growing the local tensors.
I think we did. I'm not sure because the physics literature is vast, so I'm not sure what exactly you are talking about. But I think I have an idea of what you are talking about, and I think we did. And I can point. We can talk later, and I can discuss it because we had some long and pleasant discussion with our reviewers when we were trying to publish it. And I think, please.
Mike, I don't remember the exact details, but my PhD student Claudius Hubik looked at that work and then published this strictly single-site subspace expansion. My impression, as far as I can remember, is it's really different from what Steve had proposed.
Yes, yes.
Both this mixing stuff, of course, which was old, and also this thing where he enlarged. We have now the paper from 2005, which you are referring to, I guess.
Yes, we have
It's really
comparison to
different.
this as a separate paper because reviewers were really curious about this, and we satisfied them only when we published it separately, and then this got published. Yeah. So, okay. Any more? Can I move on? Yes, please.
So since the target optimization function is a quadratic form,
Yeah.
so why do we choose? Why do you choose the gradient descent? Because actually you can solve it directly, right? I mean, with respect to each tensor.
Yes, when I say optimization, and I say here that I optimize, it's just a solution of a linear system on one side. Yes. So the minimum is just a solution to a linear problem, a one-side linear problem.
Okay, so it's not using gradient descent, some kind of algorithm.
We are computing this, so we are using a gradient descent here. Maybe I misunderstand your question here, but there are two different things. There is one-side optimization, and there is a gradient descent, which is a global step, which is a computation of a global component of a global residual. And they are quite separate. One is local. It depends on the environment, on how good your environment is. And another is trying to enrich your environment with useful information. So then you are projecting to a space which already contains your gradient directions. And you can go along with the gradient. If you are stuck in a local minimum, you at least have this local gradient direction, so your optimization is never stuck. That's what the difference is.
So I'm a bit confused, sorry. So the global optimization function or loss function is quadratic, right?
Yes.
So then you can calculate the derivative, the gradient or derivative directly, right?
Of course.
So you can solve that equation directly.
Yeah, but x is a high-dimensional thing. X is a vector which has 3 to power n states. Mm-hmm. So I cannot represent x. I can only represent x in this factorized form. And I can only work with components of this representation. I can never get x in full. I can write on paper x equal whatever, but I can never compute it because of exponential hard. Please.
Just to understand, is it your column that a low rank approximation?
Yes, it's a low-rank approximation of the residual.
Thanks.
Yes.
Okay.
And we control how low rank we want it to be.
Okay.
Yeah, and rank 2 is usually okay. I will try to carry on because this red thing makes me nervous. Okay, so we can do it for time dependent because differentiation with time is a linear operation. You treat time as a new variable, so you have a linear problem for tensor which has just one extra dimension. It doesn't change things as much. You have to be careful because it's not positive definite, but it's okay. I leave it aside. So we basically use the algorithm which I described, which we call AMAN, alternating minimal energy method. And we apply it here, and we call it time AMAN, T-AMAN. So we use this algorithm here. This is our twist. So it's familiar for you with a little twist. So, okay, people in the trade do not use it. They use Monte Carlo instead. Do you know, you probably know how Monte Carlo works. Yeah, you sample how soon the event is going to happen, and you sample what's the event going to be. If you arrive at the terminal state, you stop and restart. So you restart here, sample, and then you move between states and sample when something is going to happen and where you are going to move. So this is wonderful. You obtain all these trajectories, you average over them. Unfortunately, the convergence of these trajectories to theoretical nice curves is 1 over root n with respect to number of trajectories. So it can be wasteful, and people still use it because they have nothing better. So we want to give them something better. So that's it. Yeah. So I want to show us that it's better now. I'm not really sure that it's better because we haven't implemented it in a proper tensor tree fashion yet, but at least I can show something. This is a network in Austria, 9 sites, only 9, so I can compute everything theoretically and get the theoretical result. And here I compare with the precise theoretical result. This is SSA, the Monte Carlo, and you see it doesn't match so well the mean and the standard deviation, and particularly the probabilities of law of rare events. Yeah, they are hard to capture because this SSA algorithm travels between sites, and if it's difficult to get in the site, you may never get in the site, and then the probability is 0 when it's not, so probabilities of rare events are difficult to recover. So that's a convergence with respect to compute time of SSA, and that's the convergence of tensor train networks. You see that it's kind of better. So we think this is future, we think this is current. But we propose people to switch to that. And this is, modulo your comment that implementation is not very, very good. Yeah, so it can be probably even better. But we feel that the convergence will sort of remain. The argument about convergence will remain. So that's probably, it for this problem. We can move to harder, larger problems. So it's a small world networks, circular chains with some dense connections along the chains, and then some rewiring. And here we talk about recovering the rare events. And you see that there is some advantage in using tensor trains in recovering these rare events. Is it going to be practical? Depends on whether you need high accuracy here, really. Because if you only need low accuracy, maybe you are fine with Monte Carlo. And this comes back to our discussion about what precision people need from their algorithms. And this is, of course, very interesting. But I will kind of stop here about this problem and try to say a few things about integration, which is a completely separate problem. So am I allowed to move on? Or maybe there are more questions on this stage? Let me move on to talking about high-dimensional integration. Yeah, so it will be a little less familiar ansatz in terms of what I'm going to do, but at least the application is going to be more familiar, hopefully. So we want to recover. We want to compute a high-dimensional integral. Yeah, and these are the examples of high-dimensional integrals, which I know. You probably know so many more. But yeah, you do it every time when you project on a state, of course. But there are other reasons why people do high-dimensional integration in all these disciplines, and I'm happy that some people after me will be also talking about this in context of mathematical. Nicole Pancotti will talk about this in the context of mathematical physics. I will talk about this problem. Yeah, and you see the specifics of this problem is that we are given a high-dimensional integral. We have no idea what the variables mean. They live in a box, but other than that, we don't know what they are. So we have no idea how to connect them. There is no network, and there is no ordering. So we sort of have to assume linear and put them in some order and then try to work with this. We may try to infer the correct order, which is something we have in mind. But for now, we just order them as they are, without any particular insight on how to put this in a linear matrix product state. So we are going to interpolate the integral expression, the expression under the integral, and then we are going to sum over all modes to obtain the integral. Integration is better than interpolation because it just gives you one number. So you can compare to analytic result, and you have a very objective measure of quality. If you talk about interpolation, it's a little bit harder because your result is accurate in one place and not accurate in others. And people always tell you that where it's not accurate, it's the object of interest, and you have not done the job well. But when it's just one number, it's very objective. So I like it because of that. So if you integrate in one dimension, you have your favorite quadratures, which can converge exponentially. Yeah, you know them very well. If you have many dimensions, you try to construct a tensor product of those quadratures, and boom, it's an exponential complex problem. So it's a bad approach. Yeah. So then what do? You switch to Monte Carlo. You sample random points in high-dimensional space. Good, but slow conversions, right? So what can you do? Quasi-Monte Carlo, you compute some quasi-random lattices. So they are not really random. They just look random if you look from a particular angle. But yeah, better. But maybe can we do better? I don't know. Well, let's come back to this. Yeah, so we are going to compute part of this, but not all of them. Yeah, we compute these lines on a quadrature, but not all of them. We will select some of them in a clever adaptive way, and this way is going to be specific for each function. Yeah, adaptive to a particular function. We will be learning function as we go through the algorithm, learning these positions of the fibers, computing them, and then interpolating the whole object from this information. That's what I'm going to do. I'm going to go very quickly. So low-rank matrix, if you know rows and columns from your low-rank matrix, you can reconstruct it using this formula. Columns times matrix in the middle inverted times rows. Yeah. Then you don't need to even look at these elements. If you know some rows and columns, you can write this approximation formula. You can write it, but is it going to be good? Well, it depends on what columns and rows you got here. Yeah. Because, for example, for this example, if you got the first two rows and columns, you have accuracy of 10 minus 3. If you have last rows and columns, suddenly you have accuracy of 10 minus 2. And this is for 5 by 5 matrix. Imagine doing it for million by million matrix. The difference can be dramatic. So what is the best position for columns and rows? Well, we don't know. We know that a good idea is to get the position of rows and columns so that this submatrix in the middle, which you are going to invert, has the maximum volume of all possible 2 by 2 submatrices. There is some theorem that this is going to have you some good accuracy estimates. Unfortunately, finding this maximum volume submatrix is a non-polynomial problem, so you cannot find it exactly, but you can use it as a guiding principle. Yes, please.
So maximum volume, you just mean largest determinant?
Yes,
yeah, so
largest determinant. Yes, sorry, yes, yeah. Largest determinant, of course. Yes, largest determinant. Because you are going to divide by this matrix. If determinant is 0, you are dividing by 0. Bad idea. If determinant is small, you are still dividing by something small, amplifying your errors. Also bad idea, so you want your determinant to be large. Yes? Okay. So we can't really find it, but we can describe a greedy one-step algorithm which is motivated by this idea. So you want to find the largest element in your matrix, compute this. Now interpolation is exact on this position rows and columns. Now look at your residual, find largest element in modules in your residual, and this is a greedy optimization which maximizes your volume. And then in this example, you reconstruct your maximum volume submatrix. It may not be exactly the case, but it's always a good idea. So we use this maximum volume greedy optimization for matrices, and basically it boils down to looking at the residual and finding largest element in the residual. And if you are not allowed to look at the whole residual, you will be looking at a subset of elements in the residual, which is a heuristic algorithm. And I'm not going to discuss exactly how heuristics works. I just describe the guiding principles here. Yeah. So let's see how it works for this generalized Gaussian density. So you look at the largest element, put your cross here. Now your residual is 0, where you put your first cross. You look at your residual again, find largest element in the residual, put second cross here, and then you continue doing it. Yeah, so you continue doing it, and you continue doing it, you continue doing it. You put your cross in the largest element of your residual, and you eliminate it. And when you eliminate it enough, your matrix and your interpolation look more or less the same. And this is how the best possible approximation converges. This is done by SVD. And this is how cross-interpolation converges. And that's not too shabby. Yeah, they are not too distinct. So it sort of captures what SVD does, but without looking at all elements even of the matrix. So it's a heuristic algorithm which is much faster than SVD and almost as powerful as SVD. Yeah, so that's what we use.
Is this cross-interpolation exposed? Will it work if there's positive and negative entries in the
If
matrix? Will it work if there's positive and negative entries in the matrix?
Yes, of course. Yes, yes, yes. Residual does have negative elements. I just draw it in a, yeah. Any more? Yes.
I mean, the complexity of this.
The complexity is, I will talk about this in a second. Just let me continue. I will show you the complexity estimate, yeah? So now we are going to apply it to tensors. And maybe this part is trivial because you just separate indices. Yeah, so to separate half indices from a half, you need to find some interpolation set between them in this big unfolding. And then you continue to do it in a hierarchical fashion. And you obtain this formula where basically you have a one-side information. And then these matrices, inverted matrices, glue the blocks together. So it's pretty much like MPS, except you have a matrix in the middle, which is inverted, and you care about the determinant of this matrix very much. You want it to be big, not small. Yeah, so that's the only difference from your MPS. So this is theoretic, because you cannot really compute the whole array, and you cannot split half from a half. There are some nice estimates of the accuracy of this interpolation, which I obtained in my paper, but I'm going to skip talking about them because these things is really driving me crazy. So this is how it really works. It works as a demerge. I have two sides. I combine two sides. So I now have rank and mode index here, rank and mode index there. And I look at this small rank by size matrix. And I already have some indices computed in it. And I just add one, just as I did in my matrix problem. Yeah, so the demerge is really the key here, which makes this algorithm robust in high dimensions. So I go in a demerge way and update one cross at a time by finding one U cross in a restricted matrix, which has rank and dimension here and rank and dimension there. And this is complexity, answering your question. So it's quadratic in bond dimension. It's linear in mode sizes. And mode sizes are just number of your states for each side. And it's proportional to the number of sides. Yeah, so that's how many evaluations of tensor entries you need. Yeah? OK. So that's how algorithm works. We can also make it parallel, but I'm not going to talk about this because I don't have time. So it also works in parallel when you update all crosses at once. And what I'm going to show you is application of this parallel algorithm because it really required a lot of computing power. So application should be familiar. And now I will be ashamed because I understand it probably, not as good as many of you here. But, we have two-dimensional Ising system. And there is some critical temperature. And on the left of the critical temperature, the system looks more like this. And on the right of the critical temperature, the system looks more like this, disordered, ordered, yeah? This transition is of interest. This transition can be described by this formula where we talk about phi is the magnetic susceptibility. There are many ways of computing this. One way suggested was to compute these sums of this series, yeah? But the elements of this series are high-dimensional integrals. And the longer you move in your series, the more high-dimensional these integrals become. And this was proposed in physics literature. And then guys from mathematics, and in particular, this guy was famous for computing pi to exorbitant precision. And if you watch Simpson series, then they actually phoned this professor to check what is the 1000th digit of pi, because Meiji is reciting the pi in one of the Simpson series. So he was quite famous for doing this exhaustive mathematical computations. He used these integrals as a benchmark for what his methods could do. He simplified it. So this is a non-physical but simplified integral. This he simplified to two-dimensional integral and computed to thousands of digits. This was tough. He couldn't simplify it, so he computed it to maybe 5 digits of accuracy. So we want to compute both. as high-dimensional integrals and compare to his results. So this is the simplified integral for which we have thousands digits of, of accurate result. So that's how Monte Carlo and quasi-Monte Carlo converges, and that's how our method converge. It's a double precision. We hit the machine precision level. That's a quadruple precision. We hit the 32 digits, and that's the multiple precision when we see the exponential convergence. We do not hit anything because we are in multiple precision. Of course, it's more expensive because we emulate the multiple precision. But there was some discussion about stupidly high precision yesterday, and I think I won this competition because this is stupidly high. The reason for this is that they wanted to do the inverse symbolic calculation. They wanted to get a number to exorbitant high precision and then reconstruct the formula using some physical constants like pi and Euler's constant and so on. Yeah, and they actually succeeded for this C to reconstruct the relation to the Euler's constant, which was remarkable, and then they can prove it. Yeah, so it's just a navigation for us to prove things. 3 minutes awful. So we also computed D to 32 degrees, 32 digits. It was quite an achievement for us. Not sure if it's useful, but that's a benchmark for computations. Definitely shows that the technique is powerful. Try doing this with Monte Carlo. Show me how it goes. Yeah, we spent an exorbitant amount of energy on this, but if people continue doing this with Monte Carlo, what they're doing with Monte Carlo, they will spend even more. So we think in terms of research, it's a good use of energy. And thank you very much. That's my references. Any questions, please?
Okay, thanks for a very clear and accessible talk. Do we have some more questions? We've already had a few. Okay, yeah, Mike?
This was the first step. So the high-dimensional integral, do you force discretize it, and then you just treat the entry, the function is then the entries of the tensor?
Yes, we assume that there is some underlying quadrature grid. For example, well, it's easy. I mean, exponentially converging quadratures for your type of the decay, just choose one. If you have a function which oscillates, you choose Curtis, whatever it is. If you have, so you know how to choose one-dimensional quadrature, and it's just a tensor product of direct quadratures, direct product of exponentially converging quadratures. If you had data on all of them, you would have exponential convergence, but you don't. But you can interpolate and recover using MPS, and that's what we are doing. Yeah, so this is discrete data. We already have underlying quadratures.
And then you're just trying to sum up all the entries in this.
It's the ultimate goal, but we have an interpolation for the whole array. So had we had a different problem, like project it or compute a square of it or whatever, we would be able to solve it. So that's our benefit on top of what Monte Carlo can do, that we have an interpolation and we can answer much more than just integral. But we present just integral for comparison with Monte Carlo.
But I mean, to be clear, once you stop the tensor cross process, you now have a tensor train that's trained.
Represents your function.
Then that part you just sum up all the
elements,
right?
Yes. But the ultimate goal can be different. Yeah, the interpolation is useful in many more different ways. Yeah.
Okay, I think we have a question from the Zoom, or a few. Yeah.
So first one from Sheng Shuang Lin. Is there a theoretical guarantee for the tensor cross interpolation?
No, there can't be. It's a heuristic algorithm. I mean, give me a tensor which is one everywhere, and my algorithm will sample and find ones and believe that the whole tensor is one. And then put in a corner of this high-dimensional space just one entry which is infinitely large. And then you fooled my algorithm. I will never find it because, it's a high-dimensional search and it's just a point in a high-dimensional space. So if you have peaks, for example, in your distribution, it's bad news for me because I will be hitting zeros and never hit those peaks. I need to know where these peaks are. So no, it's not a remedy which can solve everything. It's very easy to fool this algorithm, but it works sometimes.
There's a follow-on part of that question. Do the left tensors themselves and right tensors themselves form an orthonormal basis?
They don't form an orthonormal basis in the interpolation setting for a good reason. because I'm not truncating, I'm only adding, so I don't need an orthonormal basis, but also I need an interpolation property. I need this property, so where I picked my elements, my interpolant is equal to the original data on this point. And you can only ensure it if you do it in the way which I explained. And in this case, you need some property of double nestedness of this interpolation indices, which is sort of guarantees the same kind of stability as orthonormal basis, but with respect to interpolation property rather than with respect to Frobenius norm property. I hope it makes sense.
Two more. I don't know if you want to take more in the room.
Let's take one in the room and then back to the Zoom in a minute. So, Roger, do you still have a question? Or? Yeah.
Yeah, is there a higher dimensional analog of this sampling?
This is a high-dimensional sampling.
Like this is a two-dimensional matrix. I mean, like, is there?
It's a two-dimensional matrix which represents one step in a high-dimensional process. So I'm going to loop back and forth in a demergy way over sides of my high-dimensional MPS and obtain these interpolation sets. Sorry if it wasn't clear, but this is a high-dimensional interpolation. I'm working with high-dimensional function here. And this is just one step.
Okay, then let's go back to the Zoom for one. And
What is the runtime complexity of the alternating minimal energy method?
Good question. It's linear in the number of sites. It's so you solve a one-dimensional problem on every optimization step. So it's like solving a linear system, and then you tell me what your linear system is. If it's sparse, then you have a complexity linear with the one-dimensional. So the dependency on mode size varies depending on kind of problem which you solve, and dependency on rank is cubic, I think. We had it in 2014, details escape me, but that's, if you can't do better, I will be surprised. I think it's cubic, and I think it's best you can do.
similar to DMRG for a Hamiltonian, but just with the A kind of playing the role in the complexity. So, yes, Nicola.
Here it seems that you can approximate multivariate function where you don't have any guarantee about the norm of the function itself, of any type of norm, right? It can be very big and very small, anything. In physics, normally you normalize in two norm or one norm sometimes. Does your method depend a lot on the original norm of the function? Because the final tensor will have a Frobenius norm or some type of norm that is very large.
The method doesn't. The implementation may, because the implementation is done in IEEE arithmetics, and if all your entries are underflow or overflow with respect to this arithmetics, it can't work. But, I mean, please rescale it before applying methods, and then it will be fine. Maybe it's a deeper question than I think it is, but
you don't know how big the norm is if you just
we don't know, right? But this is the thing you compute on fly, and yes, if the norm is overflow, you will have problems, maybe, but actually not in the interpolation step, because interpolation just compute elements. It doesn't care about the norm. You will have norm later problem if you try to recompress it as an MPS and enforce orthogonality conditions, then boom, you may have an overflow in your central block because all your norm is now there. But at interpolation step, you just compute entries, and blocks consist of entries of original. So everything you compute are entries. Everything you store are entries. You just do the LU on these inverse matrices, but that's the only thing you compute. The rest are just computing entries.